So we are happy to see such a faithful and very active audience here. We are doing this meetup on medical devices every other month, so be in touch. And let's start with Moshe Safran. He's our new CEO for the US. And we will introduce a little bit about our company and about our activity in the community. So, Moshe.
Thank you, Ron. So, my name is Moshe. I'm leading our US activity. Some of you may or may not have heard of our company. We're RSIP division. Basically, we're a 50% consulting firm for computer vision and deep learning applications and algorithms in medical devices. We've been around for quite a long time, for over 25 years. But we really feel just over the past few years that we're really at the right place in the right time. Really, AI and computer vision in medical in particular and in general has really been taking off and exploding. We've got a lot of things going on here. Our bi-monthly meetup, our webinar, the last one we talked about regulatory procedures for approving AI in medical devices. Of course, the vast majority of our clients and partners are out here on the West Coast in particular, and in the US at large. Yeah, this room and this crowd here is just an indication of what's going on in the field. Yeah, so we're very pleased today to host Tali Morel of Facebook AI, who's a senior applied research scientist. He's going to talk about robust, accelerated MRI acquisition using AI. And this juxtaposition of Facebook AI research and MRI is just, in my eyes, just a sign of the times of what's going on. Really, everybody's racing to embrace AI. You go to a dental conference the main clientele there are dentists, but you have medical device creators, and everybody is racing to say, I am doing AI, I am doing computer vision. I'm not only supplying a device that's generating images, I am supplying some automated interpretation of these images. You go to a TCT conference last week in cardiology, and obviously there, everybody's saying, yeah, we're really far along the road. We're doing all of these things, but really, this is the time when the medical device market in general is moving from just early adopters to really accelerating very widespread adoption of these technologies, and really everybody's trying to figure out how to get these technologies implemented, where to start, how to get these solutions approved. So yeah, we're very happy to be here. Our second speaker will be Ehsan, a researcher at Stanford University. We'll talk about confounders in medical studies and deep learning. So Ehsan will educate us about all the things that make our lives difficult. So we're very happy to have him here as well. It will be a very interesting talk. So without further ado, we'll pass the time to Tali Morel of Facebook AI.
Hey guys, yeah, thanks for coming. I'm Tully. I work for Facebook AI Research on a team called MRI. MRI project is basically a collaboration between NYU and Facebook. The researchers using AI to accelerate MRI mostly. The goal is to get up to like 10x acceleration, and also we have some other kind of future things, more robust motion acquisition and whatnot, which I'll talk about. This talk as well, feel free to interact whenever I have a bit of extra time at the end, so it should work out well. So basically, in the talk, I want to talk about two kind of main bits of public research that we have. One, which we released November last year, which is basically an archive paper explaining kind of the MRI acquisition acceleration problem, for the perspective of a computer vision or machine learning researcher. So that's the fast MRI. open dataset paper, and it also talks about like, a dataset that we released. So if anyone wanted to kind of jump in and learn about this, that would be the one to go to. And then later on in the talk, I'm going to be talking about some more recent research that was published in CVPR 2019 by the Montreal group, researching reducing uncertainty in undersampled MRI reconstruction with active acquisition. Cool. So this is the fast MRI, basically open dataset paper. So definitely, if you want to hear more information after the talk, go look this up, and there should be more detail, basically. But a lot of the tables and results that I'm showing will speak from that as well. Okay, so first of all, like why actually accelerate MRI versus some of the other medical related problems? Like why is this the one to tackle? I don't know if you guys have had an MRI, but they take maybe like 15 to an hour. It's like not really a great experience. Despite like how good it is for a radiologist to actually have this image, a lot of the time, like the people that actually are getting MRIs, maybe children or sick patients, like find it maybe hard to not move, and that actually ruins a lot of the images from all these motion artifacts. So if we can actually improve the speed of an MRI, it means we can actually get much higher quality images just like for free, basically. That also means that like for imaging organs, for example, if you're imaging like an abdomen, what they might ask the patients to do now is like hold the breath each time and quiet for some amount of time. And again, for like sick patients or like children or elderly, like that's really hard. Basically, it's hard to get the image at all. And the other thing is like compared to maybe some other medical machine learning applications, this one it's really just supplementing the radiologist's job just to help them get more information so they can do what they want, rather than like trying to just tackle the whole thing of like, let's just detect some tumor or something, which possibly like, it's arguably not the right way to approach things. Okay, so how do MRIs actually work? And this is obviously very high level, but essentially, at least from our perspective, you have an MRI scanner. It's acquiring frequency by frequency this basically a 2D Fourier domain image, which in the medical community they call K-space. If you do a 2D inverse Fourier transform for this, you're basically going to get this final image. And like at the most rudimentary like MRI without any acceleration, that could take like up to 1 hour for one sequence. I'll talk through how they've accelerated the last 30 years. So one of the first things they did to accelerate, so say MRIs came in the 70s, like parallel imaging came in the 90s. That's the idea of just using multiple coils rather than one coil, so that you can acquire different areas of the anatomy, each with having their own like sensitivity, so that they acquire a bit more of the part of the anatomy that they're closest to. Then these coils would basically just be combined into software. So just even to recap there, like basically if we had the data from one of these acquisitions, which is like a 15 coil MRI machine, hopefully you can see that, it might be a bit too dark, but basically on the left you have like 15 coils of K-space, like in the Fourier domain. Once you do the inverse Fourier transform in each of those coils, you're going to get like kind of images which have parts of the anatomy, and then on this last image is basically the sensitivities for each of those coils and like what part of the anatomy they're actually capturing. Cool. So then basically that's all like fully sampled. Then to actually accelerate, you want to undersample within the frequency space. That is to be like literally, because the MRI is acquiring frequency by frequency, if you don't sample like certain frequencies in this K-space, it's directly proportional to a speed up of the acquisition process. So say if you acquire only every second line of K-space, and that's going to turn into a 2 times speed up. So to explain how this actually works in parallel imaging, this is what nearly all modern MRI machines will do this. Sample, let's say, every second line for, like, say, 3 coils in this example, and that's going to be like a 30-minute acquisition. Then obviously when you do the inverse Fourier transform, because you haven't acquired all the data, you're going to get these like aliasing effects. Luckily, because you're acquiring every second line, you know what these aliasing effects will look like, and essentially there'll be 2 parts of the signal in the image after doing the inverse Fourier transform. So again, I'm not sure. Oh yeah, you should be able to see that. Like, there's basically these 2 red two red arrows in the middle. That's basically just one point of information, and every coil. That should be like ending up into one of the n-fun images. And so if you have like multiple coils and you know exactly where the signal is, it's basically just this linear system that you can solve and like work out, exactly what should contribute to the final image. So these methods are just called sense, and I didn't want to go into it too much, but if you ever want to look at exactly how that would work, it's kind of sense. And there's whole lots of other ways to do this. The other way that people have been speeding up things, like more than say like 2 vector space samples or like this parallel imaging acceleration, is using compressed sensing. I'm hoping that maybe some of you guys are familiar with it. Basically the idea is that like we know that MRI images have some structure, for example sparsity, in some domain. So like you could imagine in the gradient domain of the image, it's going to be sparse because there's not going to be that many edges relative to the rest of the image. So compressed sensing is the idea of like you have this prior on sparsity, and then the other key part of it is that you're doing the mask that you're using to undersample is actually a random mask. And the reason the random mask works is because if you, and some of you guys might be familiar, but if you do a random projection on some kind of vector image or signal, the Euclidean distance after that projection stays the same. And so that's basically, you can do like a random projection in some lower dimensional space, and it actually preserves a lot of information. That's kind of the intuition behind compressed sensing, the sparsity and this random projection, and then solving basically this like kind of least squares problem, which I've got at the bottom there, and then that will kind of come up with this ideal sparse solution. So just as a bit more of a concrete case, in the MRI setting, you have like some mask that you want to acquire, which basically is the subsampling mask. You actually program that into the MRI scanner, which you can do with modern scanners, particularly for these masking patterns. It's going to give you the certain frequencies that you've acquired at the accelerated acquisition that you've actually undersampled at. Then when you do this inverse Fourier transform, you're going to get like an earliest image. But then the idea is that you solve this least squares where the second term of that equation is the sparsity, T is the sparsity transform, which could be say gradient domain as I mentioned before, or something like wavelets. And then just doing like a lasso optimization, you'll basically find this ideal solution. Okay, so that's kind of like traditionally how things have been accelerated, but the question is like why sparsity? The reason is it's just kind of like a handcrafted prior that people know, images tend to have, but like, is there a better way? And basically the idea is that in the last few years at least people have been doing is learning this prior with machine learning. So formulating this machine learning problem, essentially you would have like a whole lot of fully sampled k-space, so just assume you have this data set, you could then take that k-space and simulate masking patterns, like the patterns that I said before, like for example random, take out 10 times undersample randomly in the mask. And then the idea is like finding a function that basically is optimizing for this reconstruction problem. And this like kind of could be thought of as a pretty classic image reconstruction computer vision problem now. So as like we were doing this project, we kind of wanted to tackle this, but realized it wasn't like a great data set. Particularly there's like lots of MRI data sets, but not many of them have just the exact raw acquisition of the k-space. Like a lot of them are just more of like MRI images and different anatomy. So we partnered with NYU, and it took about 8 months or so, but like we ended up collecting this massive data set, 57K images of like raw k-space that we can mask out and have the full phase and magnitude of each image, which is really quite important actually, because the acquisition, the phase, has like a pretty common pattern that we can leverage and learn from. As part of the data set, we also have this 1.2 million image like post-process just dichoms, which is basically what more the radiologist would see, but it doesn't come with the complex components. A few other details about this is it's a multi-coil, it's basically about 15 coils. for each image. We also have single coil images that we simulated from the multi-coil, which is maybe a bit easier to tackle from the start. We also have 5 different machine types and 2 different acquisition types, fat suppressed and non-fat suppressed. So I think the fat suppressed is the bottom one. So just in comparison to some of the other data sets, like the other ones we saw are 100 volumes or so, but this is going to be actually 1600 or so. Cool. So just want to talk a bit more about the undersampling pattern. For the data set, so we released this so anyone can kind of look into it. We chose to use Cartesian random masks, which are essentially these random horizontally acquired masks. There's probably better masks. The reason we chose this is that they're given like a Siemens machine, you can just straight away go and program these in. And we chose to look at like 4 times an 8x acceleration, just because that's about, 4x is kind of like the state of the art, I would say, and then 8x is what we're thinking, we can jump to. And I'll talk about a bit more about some optimal masks later. Cool, all right, so we kind of formulated the problem and have the data set. We wanted to just try like a deep learning baseline to see how it compares to, say, the original compressed sensing. One kind of common architecture for deep learning that's used is the UNet. Assuming kind of you guys know about this, it's just a convolutional neural network which has these downsampling layers to some kind of low-dimensional state, and then deconvolutions. And then I guess the key kind of novelty of the UNet is that you have these skip connections between the downsample and upsample layers to kind of help propagate the gradients through or get information to the other end. This is taken from the computer vision. Well, this is just used for segmentation and like inverse problems in the computer vision literature a lot. And I guess exactly how this will work for the multi-coil cases, you want to be able to actually combine these multiple coils to one image first. So one example is you just take the root sum squares of all these coils after the inverse Fourier transform, and then just feed that final image to the UNet. There's obviously like some issues there where like as soon as you've done a root sum of squares for the coil images, you're kind of losing the information that's just combined into. So there's obviously like other models that are worth playing with, but I'm not going to have time to go into too many more. Okay, yeah, and also like how we actually going to evaluate these reconstructions is kind of one of the key challenges I think of this problem. First of all, there's just training a model and like using an L1 or an MSE is going to be fine there. But we've been trying to use, the structure similarity seems to be the one that matches most with what a radiologist is actually going to be looking for. I don't know if you guys have heard about structure similarity. Just briefly, it's basically like a window that goes to the image and does moment matching between like the mean and the standard deviation between these two windows. And it kind of is looking more into the structure rather than like pixel-wise error, which tends not to really matter when you're looking at like anatomy, particularly these. So that's kind of the issue that like that's the best that we have at the moment, and that is like we have radiologists. Our reconstructions we review with a radiologist every week, and then we're finding that the structure similarity like for our top models, even if they all start to kind of level off, and then the radiologists have to kind of choose which models are the best. So we have like no automated way of comparing which of the reconstructions are the best. Within reason, like it still helps to get to the top, but like to compare the top models, essentially. If that makes sense. So in terms of the results of the baseline, so we have the UNet, and then we have this like classical total variation approach I mentioned before. You can see from the SSI metrics that it is much higher, and then we talked to a radiologist and it is like obviously at 4x, basically like the classical total variation doesn't really work. Like you could never do it in a clinical setting. The UNet's probably a bit before clinical, but some of the more state-of-the-art models, you can actually make it to 4x. Okay. Yeah, here's some actual reconstructions so you can see what they would look like. On the end, which actually is getting some of that high detail structure, and then the total pressure and the sparsity. How am I going with time? 2 minutes here. Okay, so I just want to just have this quick slide. Like, part of the FastMRI project, we've released this challenge, the FastMRI challenge. It's like this website, fastmri.org, that you can submit reconstructions and see how you compare. There's like links to the data sets and all the test sets, so it's really just like give it your best shot and see how it goes. We actually had a like official challenge that ended last month, where people could submit on like another test set that we've reserved, and the winners of that were going to be invited, will be invited to Europe's. The interesting thing there is, like, I know I said the SSIM metric isn't that great for evaluating, so what we're doing is we're actually taking the top 5 SSIM submissions and then giving them to a radiologist, and the radiologist is deciding which is going to be best. That's really like our way of getting around like not having a great metric. Okay, cool. And actually, just with the metric thing, it's like I think that's really a big open area of research. Like, is there a perceptual loss that better suits what a radiologist is looking for? Okay, so this is the kind of the second paper that I mentioned, and I guess it's motivated by the fact of like we're using Cartesian masks that are basically we've just chosen because they're easy to implement in the machine. But is there actually a better undersampling mask that we could choose? So this is the paper, as a CVPR 2019. Definitely take a look if you need more details later. Explain how it works. Essentially, you have so it's in the kind of area of active acquisition where you have like a human in the loop that can monitor the whole process. And so you basically start with like a very undersampled case base that you get from the MRI scanner through some initial mask. You then, if you do the inverse Fourier transform on that initial case base, you're going to get like this image in the top right that just looks quite biased. The idea is then to use some kind of reconstruction algorithm, somewhat like the UNet I explained before, something maybe a bit more advanced. But then, as well as estimating like the mean maximum likelihood, you also want to estimate the uncertainty, so say like estimate the standard deviation as well. And then the idea is like given the best reconstruction you have and the best uncertainty from that, the evaluator is trying to work out which of the measurements from that reconstruction is the worst. And this is kind of trained in this adversarial way of reconstruction trying to train the best reconstruction. Sorry, the reconstruction network training the best inferring the best images it can, and then the evaluator trying to work out what part of those images is the worst. Then the idea is that like when the evaluator can work out what is worse, it can then also work out what it needs to acquire next to make sure that the reconstruction will be best on the next loop. So it's basically this iterative process of reconstruct, evaluator working out what will be the next best measurement, and then taking that measurement. The key thing is that then you could have radiologists or like MRI technician look at these reconstructions in real time and the uncertainty maps and decide when they want to stop or when they're happy with the reconstruction. I think it's like something like this does seem ideal because it's somewhat clear that different anatomy and different images could have different acceleration rates. It's not like every knee needs a 4x acceleration, like maybe the end slices don't need as much. So I think like some kind of active acquisition process does make sense. All right, I have a bit of a video of how this works in action. So just explain the slide. I guess the subsampling mask part is basically like the case base that they've acquired. The error map is the difference between the reconstruction and the target. And then the initial impact input is also the inverse Fourier transform of the initial like zero field solution. So as you play the video, it'll basically be doing the loops of like choosing a new case base, and then you can see how the MNC changes basically over time. I might play it a few times just so you can see. So you can see the subsampling mask is kind of filling up from the sides and coming together. That's because like the ends of this case space is basically the low frequency components of the Fourier space. So it's basically progressively choosing starting kind of from low frequencies, which do tend to have more information, at least on a global level, and then progressively getting higher frequency details, which is exactly what you'd expect. The question is like, so we're using this adversarial evaluator, that's great, and it looks all good. How about just like we acquired like heuristically from low to high progressively, and like is it actually better? So we have some baselines against that. I'll just play this video again so you can see. You can see the uncertainty dropping, MSE dropping, and the evaluator getting, I guess, I don't even actually know what that means. So yeah, against the baseline, like the different compared strategies is just randomly, so you just take some random mask without really caring at all. And then just not even reconstructing, actually just doing random and zero field. Number two is random and reconstruction. So you do a random mask and then you do some network that also reconstructs it, but you're not doing like a specific case-based trajectory. And then order is kind of what I was saying before, is like maybe the logical choice of you'd think low frequency is more information, so let's just start from either end and then go towards high frequency. And then the last is the active acquisition. And so you can see, this bottom like KMA is the like percentage of case-based acquired, and then MSE is just going to be the test metric. And you can see that like basically that curve is all better than all the other these other baselines. Cool, that's all I got.
Thank you very much. So, would anybody like to ask some questions to the speaker? Okay, let's start with you.
Very nice talk. Couple of practical questions. When you're doing training, does the training data have tumors, fractures, in the abnormal situation?
Yeah, so there is, I don't know the exact count, but there's lots of pathologies. We also have pathologies that are in the training set that aren't in the test set. So just by chance, because we have so many images really. So yes.
So the question is because your method depends on structural information, which is really difficult to same for everyone. But the tumor situation will be different. So I'll be very interested how going to do tumor detection for all of them.
Yeah, I think it's fair. Like the data set naturally is just going to have more of the center of the distribution. The tail is always a worry. There is like the hope there, and I think there still needs to be some work done in terms of like uncertainty and deep learning, and that's like maybe this is still the first step. I think the only good thing about this is, like I said, we have pathologies that are in the test set, and also we have pathologies that, like, you know, the discus varies can be only like one pixel between seeing if it is there or not. And we can see us reconstructing that, so that gives us hope that they will reconstruct that high quality.
Like any thoughts on what metric you might use to assess how good you are in a clinical situation where you may be trying to detect something that's very small, that's really probably in the high frequency information?
Yeah, I think that's been one of the really the biggest challenges. I think that's like a massive area of research of just perceptual losses that make sense. You could do some kind of perceptual loss that is based more on a classification of like rare diseases. I'm not sure how familiar you are with perceptual loss, but like you could emphasize it towards what the things like that are rare or like in the tail part of the distribution. It's future work.
Any more questions? Okay, go to you.
I'm very curious why Facebook is doing
Yeah.
So why is Facebook doing MRI research?
Yeah, definitely get on a lot. Facebook AI research, really, we're trying to drive AI research in general, and we feel like this is just a really high impact area to society. There's actually a lot that can be done and a lot of progress that are already made. I think, it still has like all the same general AI research that all the rest of the Facebook AI research org is doing. Compressed sensing can be applied in lots of parts of the company, and it's more just like a vehicle that we're using to drive this research and hopefully help people.
Maybe it's because it saves lives.
That's the thing, that's the thing, yeah. So it can help people.
Please go ahead.
So compared to the compressed sensing method, what is the speed of the observe, and
Yeah, okay, that's a good question. So, in terms of what we have, like, a lot of the research we've submitted to journals and stuff, so I'm not meant to talk about it, which is why I just talked about the baselines. If you look on the website, you can see that fastmri.org website, you actually see the leaderboard of like the 4x and 8x acceleration, actually see the images. I would say that like, from people submitting, like 4x is really good, basically. Like, we're almost at the point where 4x is looking great. I think 8x we're not at yet. If you look at all the reconstructions, really no one's made it there. Of course, when I say we're there, I'm saying like we've hit some metric that looks good. I think there's obviously clinical validation, all these things that need to go through, and actually maybe 4x, it's good for 99% of cases, but it needs to be good for all of them. To your other question about inference,
Compared to the compressed sensing-based MRI acquisition that also reduces the time required to acquire, right?
yeah.
Compared to that method, is this 8x or is this compared to the traditional method?
Gotcha, yeah. That's a good point. It's about 3x, I'd say. Yeah, rather than 4x, yeah. I think correct. For the other question you used about inference time of the actual model as well, basically it turns out to be negligible, like maybe the model is takes 30 seconds or something, but when you're trying to reduce from 30 minutes to 3 minutes, it's not really the bottleneck.
Anyone else? Yes, please.
Yeah, I'm kind of curious in your acquisitions, how important is the starting point? Like, do you use particular starting patterns that are maybe built for particular body parts? Like, one brain is a lot like another brain, so a starting pattern could sort of help accelerate things?
Yeah, it's a good point. I think, so the starting point that we always used was all the low frequency lines in, because I think it's always we're starting with like 10. I think if I go back, you can see at this, where was that? You can see in the subtype of the mask it's like white at the top and bottom. That's basically the low frequency lines, and it's because they just give so much more information than anything else. It just, like, no matter what algorithm you use, I'm almost certain that would be, because I think we actually verified that is always the case. So yeah, I think honestly for every anatomy, low frequency should be the best. Yeah.
Can I ask another question?
Of course, yeah.
Have you ever considered working, keeping all of your information in K-space? So rather than doing reconstructions, just look at the data in K-space.
To do the reconstruction specifically?
Well, maybe not to do the reconstructions, but to do what, maybe that next step, what the radiologist would be doing is, looking at it and saying, oh, there's a tumor.
Yeah.
Maybe that information is embedded in K-space, and a machine doesn't really need to look at images.
I totally actually think that's an awesome idea. It's like the quickest way you could get some information is basically you're literally doing inference on if there's a tumor in there before doing this reconstruction process, which has all these issues. I think it does kind of go into this other line of work of like, rather than us just kind of trying to help the whole process of radiologists, now you're actually trying to detect things, and is that the right problem to solve? Maybe one day, but I think taking this step first is maybe the better starting point. I think it's a cool idea though. I'd love someone to try that.
That's very hard for the FDA to accept.
Exactly, yeah. Right. I mean, I think it is like there's definitely a clear path of like you have an algorithm, you do lots of clinical trials, you get FDA approval, and it's in the machine. We have something that's like detecting whatever. That process seems like, I don't know, we just receive it.
It's like magic.
Yeah.
Questions, please?
So if you train it network based on the ground truth, and you use that as your base, how agnostic is the network or orientation of the analysis? If you have your images a little bit to show the shift in the ground truth a little bit higher.
Yeah, it's a good question. So this data set is only coronal images, so it's actually only looking at them from like this side of your body. In the future, we're trying to get more data sets to have different orientations like coronal, axial, and sagittal. Then I guess there's also like even for the coronal, maybe it's slightly perturbed. It's basically all to do with like, is the data set representing the distribution of what's actually going to be inferred for? Like, I don't think machine learning is this like particularly special bullet, which if there's just a case it's never seen, it will struggle. The idea is that like, the data set will mostly capture the distribution as a whole. So it would be about changing the data set itself. And we haven't done an analysis exactly for that. I'm not sure.
How long does it take on average to train, like an average compare?
So I think the unit that we trained was only like maybe a day or something. But I can just like some of the models that we work on that I haven't already shown today, we train for about a week or so. Like and they're gigantic.
Yes, please.
I have actually kind of a question, and I apologize because I came in a little late, so I missed it.
It's fine. Yeah, but
First part of the question is, this is a 2D unit, is it, or?
this is just a 2D unit. Yeah, so that's true. Like, MRI's obviously come in, well, they come in maybe 30 slices per sequence, but we're just training on each slice.
Okay, and the second part of the question is, can you tell me what the input dimensions are for the input layer, and do you have some specific requirements in terms of the inference latency or inference rate that you're trying to get to?
Yeah, that's a good point. So in terms of the resolution, the actual data set is different resolutions from around, they're basically exactly what we acquired from the machine, so it's about 320 by 640, but we just crop all of them to 320 by 320, and that's why so all these images are about 320 by 320. In terms of the inference time, basically even our biggest models, which get up to 32 gigabytes, they're still only taking about, on really good GPUs, they're only taking about 30 or 40 seconds, which is negligible compared to the actual speed up that they create. Yeah.
30 to 40 seconds on 320 by 320.
Yeah, that's what, on like a really huge network, yeah.
Okay, so this is, I guess I can see what I'm saying, more about the network currents.
That's somewhat, except that, keep an eye, in the next 2 months or so, we're going to be released, we have a paper that we're just going to publish on this kind of stuff, yeah.
I'd actually like to follow up just quickly on that one. So it's really impressive to see how well your, what you call your unit baseline did just almost immediately.
Yeah.
I'm sort of curious about what people are doing beyond unit, what seems to actually be effective and giving some meaningful advantage.
Yeah, there's a few different ideas there. One thing that's big, there's this paper called, by NYU called something, variational network is basically what it's called, and that's probably the state of the art at the moment. And I guess one kind of interesting thing about that is it's cascading units, and then after the units you have a data consistency layer, which is given your prediction, then projecting the input back onto the prediction, because you know the prediction, you know that the input is actually has a component of the ground truth, right? So you basically are projecting back on the prediction and then doing another unit, and then you just cascade this thing. And it's kind of interesting because that's actually somewhat like what compressed sensing is doing, where you're having a gradient descent set, which is making a prediction, then you're doing a data consistency by comparing it with the input again, and then you're just doing this in a cascading way. Not sure if that made sense, maybe just read the paper, but that's some of the ideas. I think another part of it is that we're doing all the prediction here in image space and without taking into the multi-coil information, it's just root sum squares. But it's really important to make sure your network is predicting on that multi-coil data, possibly in k-space and in image space. You may have two components.
Okay, more questions? Okay, yeah, please.
So the second paper that we're talking about was the adversarial neural networks,
Yep.
and I guess were you saying the radiologist can decide when to stop, when they've got a fair enough image?
Yep.
How would they know if, say it's a really small tumor, like a millimeter or less, how do they know if they're deconstructing? You're looking at these as they get bigger, but if you're looking at it smaller, because it's smaller, I guess does the size matter in terms of
Yeah, I think that makes sense. It does totally matter. And I think the idea is that the radiologist or technician would be aware of the anatomy and the whole idea, and can make an educated choice. That, for example, there's some parts of the knee that they would really just never look at, and they can basically use that information. I think the other thing is that you get this uncertainty map as well. So you have an idea of what parts of the image it's most uncertain about. So again, if there's some part of the image that they really don't care about, and then they're kind of looking for some specific thing, like an ACL tear, MCL, then they can really just stop it exactly when they need that and be confident. Yeah.
Okay, so let's thank the speaker again. Next up we have Ehsan and Adeli, who's going to talk about confounders and medical studies and deep learning. And researcher at Stanford University. So it's very always very interesting for us, and probably for most of the people in this crowd, to hear about what we should be aware about and what we should be worrying about when we're doing our solution, which is why we're very happy to have Ehsan here.
Thank you, and thanks for having me. My field of research is mainly working on AI, machine learning, computer vision algorithms for medical image analysis, but my focus is to do interpretable machine learning algorithms to somehow provide mechanistic understanding of diseases, not to only do the classification or prediction. And then this requires identification of imaging phenotypes, biomarkers, and stuff. But today I decided to talk about part of my research, which is about confounders, which are mainly neglected a lot by different research works in the medical image analysis field. So I thought this is an important topic, and I decided to talk about this. But first, what is a confounder, and what do we mean by confounding variables? So in statistics, confounders are variables that influence both inputs and the output, the exposure and the outcome. And therefore, when you want to create an association between the input and output, you're actually having some type of spurious or distorted association. And in many works, we've seen that people build up deep learning networks, methods for doing disease diagnosis, predicting or classifying things. And if we are ignoring the confounders in the studies, we are actually probably getting distorted associations, and they might affect the final understanding of the disease. So let's say we want to build a model, and I'm just trying to give you a very easy example. Age is a simple confounder in almost all medical studies. And this is a work we've done last year, in IPNI, actually this year, which is an analysis on age, on aging effects in the brain. And the input, the brain image, is actually affected by the factor age a lot, and we know that. But at the same time, there is a huge effect on the diagnosis part. So, for example, consider you want to predict an Alzheimer's disease, which is now a very popular topic in medical image analysis. But we know that Alzheimer's disease affects different people at different age ranges differently. Or another topic that I'm working recently, HIV diagnosis. We again know that the age distribution for subjects is different. So age is actually a very, very strong confounder in almost every study we have. Another example is, again, based on the same idea of age being a confounder, is you are comparing two groups of disease and control. And one might have a different age range, or might have like larger or smaller values for age in the subjects. For example, here disease group is mainly older than the control group, and this is very much probable, even in the public data sets that we see always these age differences. And if we learn this deep learning network without considering age as a confounder, we're actually learning the effects of age on the brain. Like, look at these difference between the two groups. So, and as we know that age affects the brain significantly, so we are actually learning the effect of this age. So it's not just age, any type of demographic information patients have, subjects have, could be counted as one confounder in the studies. And other than that, treatment procedures, drugs that they use for treatment, and even disease comorbidities are important confounders in all types of studies when we want to predict or classify based on inputs, MR images or medical images of any type. All right, so what we used to do traditionally was using statistics, and there is a very large field of different methods. One of them is a stratification. You group the subjects based on the confounder variable that you're looking at, and then either try to build a model for each of these clusters, each of the clusters separately, or at least give the cluster information as another important factor in building a model. But the thing is that it's making the data smaller, and kind of it's not very practical in medical, in deep learning application. I'll talk about it. The more popular way that neuroscientists and medical researchers they used to do and still are practicing is using something like a residualization. And what they do is they build a linear model based on the measurements they have. They extract the measurements from the brain. And for example, ROI, regions of interest, volumes, or any other types of measurements that you can use in a study. And then what they do is they build a linear model with the confounder and the measurement, and then they residualize the distance between each single sample and correct somehow the value of the measurement. So this is a very, very popular way of solving the problem, at least looking at the problem, considering the problem. But given that with deep learning we try to do end-to-end training, we are looking at voxel values, at pixel values. So it's not doable. We can't use the same type of visualization. We can't use the same type of statistical method to create some linear models to residualize the values because of many different factors. If you have any questions, I can talk about it. So, in order to look at this problem, solve this problem in a way that we can understand the results, we can look at the mechanistic understanding of the diseases instead of effects of variables. I worked on some projects, two of which I'm going to talk today. One is on using some techniques for visualizing deep networks which are aware of the confounders. The other one is actually training a network that is free from the confounders we know of. So both of these are very, very recent works. presenting one of them in a couple of weeks in MRI, and the other one is going to be out in archive in a couple of days. But that's under review right now. So the first work is about confounder affair visualization of convolutional neural networks. So we train a network to classify this input image I to an output diagnosis. And what deep learning does is often some feature extraction steps. Mainly they are convolutional neural networks. In this case, convolutional layers. Sorry. In this case, we're using 3D convolutional layers. They extract some features. We call them feature here. We have feature maps at the end of each layer, but at some point we flatten them to do the final fully connected classification part. So these features, then we use some layers for classifying the data, and it gives us some score that we, at the end, threshold and say what is the outcome, 0 or 1 or whatever. So this is an end-to-end predictor training. So in order to understand, so you know that in all these deep learning methods and with the recent developments and libraries, we can simply visualize the saliency maps in the input image, like how this outcome was created based on which parts of this input image, layer-wise backpropagation. But here what I'm trying to talk about is not that part. We're using the same type of layer-wise backpropagation, but we want to know which of the features that we learned are affected by the confounders, say age. So we look at this SI and FI as features and the outputs. So we built a GLM model, generalized linear model, based on the confounders, Z, the score S, and the features that we learned. Statisticians, they know that this linear model, we can have a p-value for each of these betas to see how significantly they are related to this feature, and then based on the p-value, we can know how each of the features are actually creating a confounding effect on this specific feature. So what happens is, based on that, for each of the features, we can create a binary network, binary vector, a BI. This BI tells us if that specific feature that we learned is confounded by that confounding variable we have or not. And then we add a layer here by using that B network, vector, and then through this layer we do a partial backpropagation, which somehow filters the features that were confounded. So we know that we have this chain rule, and based on which deep learning is built. And then with partial backpropagation, what we do is we incorporate the B vector that we created to mask out some of the features. Then at the end, we create a visualization on the brain, the input brain, and that visualization does not have the effect of the features that were confounded. So then this can be used for some understanding of the disease and outcomes of how the brain was different, changed, that somebody was diagnosed by this diagnosis. We did several experiments starting with synthetic data to validate what we did. We created some random images by creating Gaussians here, and then trained the network. This was the output of the network to predict the the two classes that we created. I'll talk about it, how we created classes. So we had 4 Gaussians here, and for regions A, B, C, and D, we created them with different with different lengths, with different standard deviation on the Gaussian. And then we created A and D to be deterministic of the class. We created 2 classes with different standard deviations, but these regions B and C were somehow confounder variables, variables that we didn't want the predict to be the network to predict them. So we did the analysis, and based on the results, our network was only showing block A and block D, the yellow part, as the parts that were affected by the decision. So here, this is the output of our network. Considering regions B and region C, like the standard deviation of those 2 Gaussians as confounders, we were able to remove that. So then, based on that, it's now very simple to look at different conditions. We looked at HIV with the data we have at Stanford, where here the data was somehow somehow confounded by age, because the age difference between the 2 groups is significantly large. So then what we did was we created same effect, same network, and then this was without our model, but with the confounder-free module that we created, we could do this visualization, and these were the regions that were actually very much affected by age and not by that specific disease that we were looking at. If you look at that region, for example, those regions that you see there, they are partly in the ventricles, and this is very much affected by age. If you remember the first slide I had, ventricles get larger and larger as people age. So if we didn't consider the confounder age here, we would be going with this heat map, and then we'll be trying to create therapies for HIV based on or at least preventers based on this output. So same experiments we did for sexual dimorphism based on Encanda. It's not about detecting any kind of disease or predicting any kind of disease. Here we were looking at individuals, healthy individuals, and we were trying to predict if they are a boy or a girl, only based on their MRI image. So one of the large confounders we saw was pubertal development score, because these are young individuals and puberty is different between boys and girls in the very younger ages. So then that was the outcome of the analysis, and these frontal regions and these parts were the difference between the 2 groups, 2 cohorts. Same type of analysis we did on the ABCD data. Encanda and ABCD, they are 2 public data sets, mainly on adolescents. And this is, ABCD has a very large population. Actually, we ran, you see it, we have 4,000 subjects from each group. The database is larger than this, is growing as we go. But what we did with this data set was actually, we organized a challenge with Minkai, again 2 weeks from now, where we asked the participants to predict the fluid intelligence of the kids only based on their MRI image. If you're interested, I can talk about it, but since it's not the focus of this talk, I'll just pass. So here the visualization gave us some similar factors, and then the interesting finding that we saw here was that PDS, pubertal development score, was affecting the cerebrum very much, which showed that in that age range of 9 to 10 and a half years old, that's part of the sex difference between boys and girls, which for us was an interesting finding. What we did was, as I told you, I'm very much interested in understanding the factors. We continued by visualizing the top 10 regions based on the deep learning heat map that we created. The confounder removed heat map. And then we looked at the regions that had the highest saliency values, and those regions were the ones that I'm showing here. And we looked at their differences between boys and girls in terms of volume. And out of 10, 6 of them were significantly different between the two groups. And interestingly, what he found was in the literature, like this amygdala was always found as a very important region for distinguishing boys and girls, but it was not significant in terms of volume. We've seen some studies, they were working on shape analysis instead of looking at volumes. They looked at curvature and shapes of the region. And that was a main deciding factor that was different between boys and girls. But with deep learning, what we are doing is just giving the whole image into that error blender and asking to classify. And then considering every factor, this was the outcome. But the question here is, what I presented to you right now was how to visualize a network that is learned. But how can I learn a model that is not just visualizing, is reliable in decision making? Even the decision it's making is not confounded by those variables. So the solution is to predict models, build models that predict target outputs while they are not somehow predicting the confounding variables. So now what we try to do is something like this, which will be introduced in the second work that we did. So here we have again an MRI images, MRI data, and we want to learn a deep model to do the prediction, but a prediction that is free from the confounder. So what we did was, again, same type of feature extraction, some features, the classifier classifies and does the classification. But what I want this time is, and the classification is like backpropagated all the way, called classification loss. What we want is those features should not be affected by confounders. So we added a module here and another network that predicts the confounders and is trained to predict the confounders as best as it can. Then what happens here is that the feature extractor part is trained adversarially. The feature extractor part is trained to classify, but be agnostic to the confounders. This part with the negative sign is the adversarial loss that is being backpropagated from this side. So this is very much similar to what people do in generative adversarial networks, or probably you know the domain adversarial models. But here we are using it to learn features that are invariant to the confounders, but why they are being a good predictor of the classification that we want. We designed this loss functions very simply. Classification loss is just a cross-entropy loss. The second one is, actually we designed a new loss function based on correlation instead of predicting the exact value, because here we want to remove the correlation. We're not trying to predict the exact value of the confounder. And then this turned into a min-max game, as in all GAN models. We named this as bias resilient neural network because it's trying to inject resilience towards any kind of bias to the feature extractor part. Again, same type of experiment on synthetic data. Here I'm showing you the diagram in terms of this value here is the correlation of the learned features as a function of the iteration in deep learning. So number of iterations, distance correlation is the correlation of features, and the output confounders, the exact confounder. So we trained a simple CNN model. The CNN model is just doesn't care about the confounder. It's always very high correlation with the confounders. While our method, it starts with high correlation, but then tries to inject that resilience that I was talking about. And we tested it with a different loss function, like a MSE, because this is a continuous variable. And this is a continuous variable, so we instead of correlation, we try to see if mean square error is giving us a good output or not. But the output of the mean square error is very inconsistent, as you can see. The other test that we did was this baseline CNN model created this feature space. So we projected the high dimensional feature space to a lower dimensional space, and you can see that the effect of this sigma b is actually there in the feature space. Same for when we train based on MSE loss function. This MSE loss function, because it's trying to put all its effort to predict the exact value of the confounder, not to remove the bias to the confounder. While our network successfully removed the effect of the bias in the feature space. So the feature space is not having any kind of effect towards the confounder value. Same story, we did this experiment on synthetic data, which we added two variables of age and sex. One is binary, one is continuous. Again, same type of results we obtained. I'm not going to spend time on it because we discussed earlier the hardware kits. The other model that we trained on was the same data of HIV that we had. And here, again, our baseline was a 3D convolutional neural network, our network with the MSE adversarial loss, and the final VRNet that we trained. So basically what happened here is, as you can see, the correlation of the features and the confounders, again, is going down as we go. This is the feature space of the baseline CNN. Again, you can see the effect of age from 20 to 80 plus years, while our feature space is very much well distributed across all ages. The interesting thing is that while we did this work to only and only remove the effects of confounders, the results also improved. And we saw this as a type of regularizing the deep network. Because all machine learning models, they are very much prone, and actually they try to cheat if there is something, some easy signal in the model, they capture it and overfit to it. So by that bias resilience that we created, we actually did not let the network to capture that easy thing. Try to find other features, and those features are better in the testing. So this is a 5-fold cross-validation setting. And this is again another visualization. And as you see, again here, we are on the ventricles, which is the effect of age on the data, while our model does not have that. I'm going to stop here. I talked about two models. One, how to visualize a network that is trained before, and second, how to train a network from scratch that doesn't have those type of effects. I just want to conclude and say that this is an important topic. Confounders are having create mixing effects in the studies, in the results, and they distort the true relationships. Thank you very much, and if you have any questions.
Thank you. Thank you very much. I think it's very important such depth analysis of the data and the thread that we have over the data before we try to find the best solution for clinical data. Because we know that it's very hard to get the right data. It's easy in the laboratory, but when we come to clinical side, it's very complicated. So thank you very much. So if you have any questions. Okay.
So if you're doing like a machine learning to analyze medical images for diagnosis, if you suspect something in the image is confounder, but you don't really know where it is, how do you tease out that confounder so that you can remove it from your analysis?
Okay, that's a very, very good question. This is a very hot research topic by itself. What I talked about today was mainly confounders that you know of, or you have data for. There are, especially I've seen several papers this last year, Europe's, that they will try to reason about like confounders, if there is any variable in the vast majority of like huge amount of data that you have that is posed as a confounder. But right now, as I told you, we identify confounders based on the variables we have, and we do simple statistical tests across groups to see how the difference is, and if difference is again based on the single p-value. But if it's significant, it's counted as a confounder. But that's exactly a very good question. That's definitely a very good question, and there are many reasoning works, like graph reasoning, creating some graphs of a constellation of the variables we have, and then look at the graph, see if you have linear and non-linear relationships, because confounding effect is not only linear, it can be linear and non-linear.
Problems that we tackle, right? And other application you have potentially look at is so many different clinical trial outcomes. And a physician, they don't even know those now. So somehow neural network or artificial intelligence can grab those information automatically learning and modeling. That's a big part of confounders.
Exactly. Thank you. There are two steps: identifying confounders and then learning models that are agnostic to confounders. The thing is, the visualization that I showed is the way that neuroscientists used to be doing it before. What they do is, they still do it, I mean, it's not just before. What they do is they remove the effects of confounders from the variables and then do the study on the removed effect variables. But then this is not applicable in deep learning, because in deep learning we want to train end-to-end. There is no measurement out of the images. We just want to train something out of the images. And I can't look at the voxel values and remove confounders, because voxel values have meaning in a neighborhood. I can't remove effects on the neighborhoods of images. So those statistical old methods, they are very good if we have engineered features. They are not applicable to end-to-end deep learning models, and that's why we were trying to get it out in the middle of the network.
So thank you very much. And you're most welcome to consider if someone from your company can come and speak about technology that is not without disclosing all your secrets, but still to give some visibility to other part of the medical imaging. So thank you very much for the very good lecture today.